All right, so the last time we talked about this idea of matrix reduction. It's like for a boundary operator, which represents all the boundary operations for simplices of all different dimensions. And we do this, it's like with respect to a particular ordering of the simplices, which respects the filtration property as well as the subcomplex property. Okay, so and towards the end of this, we talked about how then looking at the number of zero or non-zero columns corresponding to chains of a particular dimension then give you information about the rank of the cyclone boundary groups. Okay, and as a consequence of that, it also tells you what the Betti numbers are. It's like by taking the difference of these two things. So now what I want to do is to talk about how you can then extract more information from this reduced version of the boundary matrix and how in particular it pertains to persistent homology. Okay, so this is the notion of pairing. So sort of in the reduced version of the boundary matrix. Okay, all right, and again how it impacts this question of persistence. So in addition, sort of to just the homology of the complex K, right, we can also sort of extract information about persistent homology. Okay, and the way it's like where all this information is encoded is in this idea of the lowest ones in each column. Okay, so this turns out to be encoded in the lowest ones in each column, or for each column. Okay, and this, might actually be surprising, and the reason is because if you look at the algorithm it's like which we presented, right, it's easy to convince yourself that there isn't necessarily a uniqueness to this reduced matrix R, right? So this is true. So that despite the fact the reduced matrix is not unique. Okay, and how do we see that? So the reduced matrix, well, I shouldn't say maybe is a bad way of saying a reduced matrix R, right, is characterized by the following. That it is reduced using sort of left to right column operations. But the point is that once it's reduced, okay, okay, you can still continue to do these left to right operations, right? Without changing the fact that it's reduced in some sense. Okay, so it's not immediately obvious. I think the point basically is that it's not immediately obvious that this notion of the lowest one associated with each column then is well defined and unique in that sense. So one needs to show that the lowest one sort of are well defined in some sense, right? Okay. All right, so how do we do this? Okay, so let's see how we do this. So I'm going to consider a submatrix of this matrix R. So we consider sort of the lower left submatrix. Let's call that R ij of R, right, whose corner is just the entry Rij. Okay, so you have a matrix R, right? There's an Rij here, all right, and you're looking at this piece, which I call Rij. So this is obtained by deleting the first sort of I minus 1 rows and the last n minus j columns. Right, so you delete these, right, 1 to I minus 1 of the rows, right, and you delete basically j plus 1 to n columns, right? Okay, so all right, so that's should be fairly straightforward so far. Okay, so that's what we call R subscript I superscript j. And one other observation is that again, we're doing these operations. It's like where we add columns from the left to the right. Okay, so left to right column operations sort of preserve the rank of each of these submatrices. So what that means is that if you do sort of the same kind of construction where you take the lower left submatrix associated with the boundary matrix, right, that the rank of this Rij submatrix is going to be the same as the rank of the boundary Ij submatrix defined sort of in the analogous way. Okay, so this means that the rank of this Rij is equal to the rank of the boundary matrix Ij. It's like where, again, you know, it's like boundary Ij is defined sort of in the obvious way that it's the sort of lower left submatrix. It's like of the boundary matrix, you know, where the sort of the corner is the boundary Ij. It's like entry. Okay. All right. So, okay, so this is the observation. All right, then you consider the following. Okay, so I'm going to look at what I call R sub R at I of j. Okay, so this is going to be the rank of Rij minus the rank of Ri plus 1j plus the rank of Rj minus 1 I plus 1 minus the rank of Rij minus 1. Okay, so if you look at this, maybe would remind you of this sort of thing which we discussed. It's like when we were talking about persistence diagrams, right? And how persistence diagrams are related to the, it's like the sorry, it's like, yeah, how persistence diagrams are related. It's like to sort of the Betty numbers, if you will. It's like associated, it's like with persistent homology. Okay, so so we'll sort of see, it's like how that shows up in a little bit. Okay, so let's just say the following. So the observation is the following, right? So if the rank of these submatrices are respected by column operations, that means that if I define the same kind of thing, it's like where instead of R I have the boundary map, sort of the boundary matrix, I would get the same thing. So by rank preservation, right, we know that Rij is equal to our boundary Ij. Again, sort of, with the obvious thing where you replace big R with the boundary in all of these things, right? Okay. Yes. So let's see what this represents. And again, if you sort of look at these things, it's like, and you go back to look at the expression we had, it's like in persistent homology, you might be tempted to think there's something that's going on there. Okay, and indeed that's going to be the case. Okay, all right. So let's observe the following. So observe that sort of the linear combination of any collection of non-zero columns in Rij is again non-zero. Okay, so what this means that the rank, so the rank of Rij, right, is equal to the number of non-zero columns. Right, and again, if you recall, it's like this has a little bit to do with, it's like the ranks of the cyclone boundary, it's like groups, right? And this is sort of the observation it's like you would get from just even doing matrix reduction, it's like for the pure homology case, right? Okay, so Now, so let's look at this Rij entry. So if Rij, right, is a lowest one, what does that mean, right? Then that means that Rij has one more non-zero column than the other three matrices, it's like which we see in this expression. Submatrices. Okay. All right, so it's one more. Okay. And essentially then what will happen is that Rrij is going to be 1. Okay. Okay. Rrij is equal to 1. Okay, maybe I should write this down somewhere here. So Rrij is equal to the rank of Rij minus the rank of Ri plus 1j plus the rank of Ri plus 1j plus 1 minus the rank of Rij minus 1. Okay. All right. So that's one of the cases. So then the other case is when Rij is not the lowest one. So if Rij is not the lowest one, then there are two possibilities. Okay. So the first one is that is that none of the 1 to j minus 1 columns has a lowest one in row I. Okay, in which case that means that so this is going to be expressed in terms of the number of non-zero columns, but the rank is related to the number of non-zero columns. So I'm going to write this as the rank condition, that the rank of Rij is equal to the rank of Rji plus 1. Okay. And similarly, the rank of Rij minus 1 is equal to the rank of is equal to the rank of Ri plus 1 j minus 1. Okay, so if those two are equal, those two sets of things are equal to each other, then you can check that Rij is equal to 0, which implies that Rij is equal to 0. Okay, so that's one case. Let's look at another case, case 2. So the other case is that one of these 1 to j minus 1 columns has a lowest one in row I. So one of these columns has a lowest one in row I. Okay, then then what happens is that rank of Rij, right, is equal to the rank of Ri plus 1j plus 1, as one more non-zero column, and that the rank of Rij minus 1 is equal to the rank of Ri plus 1j minus 1 plus 1. Okay, so again, in either case, it's like what will happen is that Rij is equal to 0. Okay, all right. Okay, so right, so in both of these cases, it's like we have that Rij is equal to 0. It's like if Rij is not the lowest one, and then Rij, and then Rij is equal to 1 if Rij is the lowest one. Okay, so this essentially establishes an interesting connection between the lowest ones and sort of this computation you have here, right? So why is this significant? This is significant now because we've expressed everything in terms of these ranks, and these ranks now are independent of which reduced matrix you have. Okay, so the observation is basically saying that the lowest ones, right, can be characterized in a way which doesn't depend on the choice of reduced matrix which you have. So let me just sort of state that as a remark. So this gives you, so this provides a characterization of the lowest ones that is independent of the choice of reduced matrix. So it is well defined in that sense. Okay. All right. So let me state this as a lemma. So that's what's called the pairing lemma. Okay, so we have that I is equal to low j if and only if, right? This reduced, this sort of R boundary, right, of ij is equal to 1, right? So in particular, the pairing between the rows and columns defined by the lowest ones. In the reduced matrix, doesn't actually depend on R. It actually just depends on the original boundary matrix. Okay. All right. So, all right. So the next obvious question is, well, what do these lowest ones mean? So the question is, what do the lowest ones mean? Okay. And again, it's like the formula you have, it's like for this R boundary and R, it's like entries, it's like looks suggestively close to what you see in sort of, it's like the formula we have, it's like it shows up in persistent homology, right? And again, we know that the ranks of these submatrices, give you some information, it's like about the cycle and boundary groups. So it is tempting, if you will, to believe that these lowest ones give you some information about, it's like the entries in the persistence diagram. Okay, and we're going to show that that's indeed the case. Okay, so you observe that column J reaches its final form right at the end of the Jth iteration of the algorithm, of the outer loop of the algorithm, right? Right, because if you recall, it's like the loop sort of goes through, it's like, the columns, if you will. Okay? All right. And it starts at the first column and then goes to the second. It's like, and it adds stuff, it's like to the left of it to that column. So once you're past that Jth sort of iteration of the outer loop, it's like you're not going to add anything to the Jth column anymore. All right. So, all right, so we have so once you've completed, it's like this Jth iteration, we have the reduced matrix for the complex consisting of the first J simplices in sort of the compatible ordering, right? Okay. So then we want to distinguish, it's like two cases, which is what happens to that Jth column, whether it is just a zero column or it's a non-zero column. Okay. So then there are two cases. All right, the first one is that column J of R, right, is 0. Okay. Then we say that sigma J, right, is positive. Okay, what is meant by that is that since its addition creates a new cycle, and this gives birth to a new homology class. Okay, all right. So basically is that after you do the reduction, it turns out that the Jth column is 0. That basically means that you've created a new cycle, which is not the boundary is something, okay, and so that's sort of a generator of a new homology class. And then the other possibility is that you have a non-zero column, in which case there's a lowest one, right? So case 2 is that column J of R is non-zero. So what it does is that it stores the boundary of the chain sort of accumulated in column J of matrix B. And is therefore a cycle. Okay. So this is this sigma J is negative because its addition sort of gives depth to a homology class. So, all right. So this tells you it's like when a particular cycle dies, right? But we still haven't talked about what the significance of the lowest one is, right? And as you might expect, the lowest one, I mean, you've already talked about when a cycle gets born, when a cycle dies. So you expect then that this lowest one is going to tell you when this cycle which just died was born, okay? So, so in case 2, the cycle represented by column J dies, right? So you want to show that it was born when the simplex sigma I, where I is equal to the lowest one of column J, was added, right? Okay, so this is true. This is clear because the cycle in column J of R just died. And all other cycles to die with it have ones below row I. Okay. So if this wasn't true, right? If this condition wasn't true, that all the other cycles die with it have ones below row I, then you can further row reduce the matrix. Sort of further reduce the matrix. to obtain that the low of j is less than I, which is a contradiction. So it contradicts the assumption that the matrix R is already reduced form. Okay, so what this then tells you then is that this sort of lowest ones are giving you information about the entries in the persistence diagrams, right? The points in the persistence diagrams. So the lowest ones sort of correspond to points in the persistence diagram. Okay, so more precisely what I mean by that is that if you have AI aj is a finite point in this diagram, okay, if and only if, right, I is equal to low j, and sigma I is a simplex of dimension p. Okay, all right. So here sigma j is a simplex of dimension p plus 1, right? Okay, so this is if you have a finite point, and if you recall, there was also the possibility of things which were created which never died. Okay, so we have sort of AI comma infinity in the diagram PF, right? If and only if column I is 0, but row I does not contain a lowest one. Okay. So this means basically that sigma I is positive. Right. Sigma I is positive. So that means it was created, right? But it was not paired with a negative simplex, which means it never died. Which is exactly what you want. It's like you have a homology cycle which was created, but it persists, right? All right, so okay, so now again it's like it's like what it takes to compute persistent homology using this reduction algorithm, and again in particular it's like this reduced matrix R, and in particular the lowest ones, it's like in it encode the persistence diagram in all dimensions, right? So let me just stop here. Thank you.